Here we go. Welcome, ladies and gentlemen of the world, the internet. Listen and behold, we are talking today about the comparison test to determine convergence or divergence of series. So we talked previously about the ratio test, which sometimes had inconclusive results. And we need a method or a means to determine convergence in such cases, and perhaps other ones as well. Maybe it's easier to figure this out. But before I get into the comparison test, we're going to first try to discover whether or not this particular series is convergent. This is referred to as the harmonic series. Harmonic, like harmony. Harmonic series. Here we are. Oh, come on, don't lose my letters here. That's good enough. All right. Looks like it's some weird double dot I there, but that's fine. Naive. Yes. Yes. So this is a harmonic series. Could someone tell me what the a sub nth term on this appears to be?
1 over n.
Right, that appears to be 1 over n. And the a sub n plus 1th term would be 1 over n plus 1. So let's just do a quick ratio test, super quick. All right, super quick. So limit, I might not even write limit all the time on this. We'll see what happens. So r is going to equal the limit blah, 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 blah. I think this is going to, yep, I'm seeing it right here already. So you don't have to write down this particular approach right here because this is going to fail. So this would be 1 over n plus 1 times n over 1. So that's limit of n goes to infinity of, I'll end up with n over n over n over n plus 1 over n, blah, blah, blah. And I'm just fast forwarding super quick here. And what are we going to find? Blah, 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 blah. That'd be 1 over 1 plus 1 over n. And 1 is going to 1, 1 is going to 1, 1 over n is going to 0. And this whole thing is going to 1. And therefore, since r, not absolute value, is equal to 1, the ratio test is inconclusive.
Well, the absolute, but clearly it's convergent because it's decreasing every time.
Well, that is what my instinct would have thought as well. Because I'm like, yeah, these are getting smaller, right? You know,
No.
a half, a third, a fourth, a fifth. Right, but I mean, even technically our convergent series, even those ones are getting bigger. They're getting bigger just towards a number, right? In like smaller and smaller amounts. So this one is an interesting thing.
Harmonic series, arithmetic series, and geometric series.
Yeah. And it turns out, watch this. If I group, nope, I lied. If I group this and this and this, if I do this interesting group strategy, so I get 1 plus a half, so that's 0.5, right? A third plus a fourth, 7/12, yep. I'm going to just do decimal representations for these. Nope. I get 0.583 repeating. And if I add these, 1/5 plus 1/6 plus 1/7 plus 1/8, I get 0.63452 blah, 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 blah. Non-repeating it. Well, maybe it repeats later, but not necessarily, actually. Now, what if I showed you this list? Would you say that I'm getting smaller and smaller values?
No, it's smaller and then bigger.
Smaller and then bigger and bigger and bigger, depending on how those happen in group. So it turns out, I mean, this is a really subtle series, I think, but it turns out the harmonic series is divergent.
Harmonic series are divergent.
Yeah.
Holy crap.
Yeah, so I just want to point out, like, this isn't always what it first seems, you know, like maybe when you first glance at this, I mean, I would have looked at that and been like, yeah, those are all getting smaller, right? Like, yeah, it's got to be, right? But no. So that's kind of an interesting case. And what we're going to do, because not all the time do we have an interesting little trick like we had there, but what we're going to do for series that we are unsure about, we're going to compare them to some known series, okay? So check this out. So here's some known convergent and divergent series. What is this? You don't have to write all this down necessarily. Maybe some of them you will, but what is this top series? What would you call that one? What kind of series is that top one? Besides convergent. It's geometric. I wasn't being very clear with my words, so don't.
That color is not.
Yeah.
Go with the darker color.
Yeah, tell you what, I don't often use black, but that's geometric. What is series number 2 like? What's that, what kind? That's, well, the eraser might actually erase it to white, I believe. A good call. Unless I was erasing with a layer, but I didn't get my hatchery tech up to layer, so that didn't work. So let's see, series number 2, what kind of series is that? That's also geometric, right, with R greater than 1. What kind of series is series 3? Arithmetic. Actually, arithmetic reminds me of, what's her face, Eris from Final Fantasy VII. Anybody? No spoilers. I won't spoil what happens to her.
I have never seen Final Fantasy.
Anyways, and then we've got the Harmonic Series, which we just found out was Divergent. So that one you might, well, I don't know if you want to write that down or whatever. These are also, by the way, found on page 789 of your text.
Arithmetic series always convert to divergent.
Yeah, because even if D is negative, then it's going to be approaching negative infinity, and you're adding infinitely many numbers that are getting more and more negative. So yeah, that would be the case. And then here's this series. So this is kind of like the harmonic, except I'm raising these to a power, right? So even if P is like 1.01, it turns out the harmonic series would be convergent in that case.
But what if P was equal to 1?
Then it would be the harmonic series itself, and it would be divergent. So I just want to point out, like, this is like really, those are like borderline right there. Like the harmonic is like so close to being convergent, but then nope, infinity. It's like, you got me there, harmonic, right? So what we're going to do, this is our general strategy, all right? The idea of the comparison test, and I don't think you necessarily need to write this down. Ah, no, I got the blurries. It was working a moment ago. Why? No, you don't have to write this down. But this is the comparison test. I'm going to summarize this with my words. And you could always refer to this video later, right? So, comparison test. This is the idea. All right, lots of words. Don't lag out on me now, lag top. So let's see. A series of positive terms is convergent if for n greater than 1 each term... All right, let's explain this. Basically, this is the idea. I'm going to compare some unknown series, all right, some series that I don't know whether it's convergent or divergent, and if it turns out, if all of its terms, for at least the terms bigger than 1, all right, the first term, if all of its terms are bigger than a already known divergent series terms, then it must also diverge. And if all of its terms are less than an already known convergent series terms, then it must also converge. Basically, it's saying if this is bigger, if my series is bigger than a divergent one, it's also going to be divergent, right? Like if all my terms are bigger than terms that add up to a number like infinity, right, then it also adds to infinity. Or if it's smaller than a series that adds to a finite number, then my numbers must also add to a finite number. So it's a matter of like comparing. Is it smaller than that or is it bigger? And then you're able to make a conclusion of it being convergent or divergent. Now technically, then it would be inconclusive because I didn't compare it to something that would have told me any valuable information. Right? I mean, I could say, my series is less than the series where each term is just infinity plus infinity plus infinity plus infinity. Like, that wouldn't tell me anything valuable about my series because it's like, oh, well, you know. So that's the idea behind the comparison test. So let's actually do this. Let's do this, people. Let's do an example. All right? Example. Use the comparison test to determine whether the series is convergent or divergent. So let's say this is my series. 4/5 plus 4/7 plus 4/9 plus 4/11 plus ... Okay? So, sometimes it's valuable to figure out what the nth term might be on this. So, what appears to be a sub n? Any ideas? The numerator appears to be 4. I found that pattern pretty good. What is the pattern on the denominator? 5 plus 2n? Okay, so how would we have to modify that? Yep. I'm not sure, like, yes, that works. I'm not sure how you're perceiving that each time. 3 plus 2n would work, right? So, well, like, you see the pattern in a different way, which is perfectly fine, right? I mean, a lot of times mathematics is like that. Actually, that was a problem that I had as a very early math teacher was, I mean, I'm still pretty young at it, but I would see math in a particular way, and that's how I would explain it, and then, like, none of my students would be like, what did that come from, right? So now, like, I actually, like, I'm a little bit better at trying to see things in multiple ways and trying to figure out which way is the easiest to explain. But yeah, so these are increasing by 2, so it's going to have something related to 2n, and if I do 2 times 1, that's 2. 2 times 2 is 4. 2 times 3 is 6. It appears as though I'm always off by 3. So 2n plus 3. I just have to give it kind of an offset, and that ends up working. Yeah, it appears to be the case. So now I'm going to want to compare this to one of these series. Okay? Now, actually, let's verify. Are these getting smaller? Yeah. All right. I mean, I'm dividing a number by a larger and larger number as time goes on, which is going to give me smaller and smaller values. So yeah, so these are getting smaller. So it's...
Should we test to see if it's harmonic?
Yeah, I think that's what we'll want to do is check it against the harmonic series. Is likely what we'll do. Now, I guess, well, that's my question. Could I prove that it's greater than the harmonic series, or could I prove that it's less than this convergent series? Those are my options. So, what do you suspect? Do you suspect convergent or divergent for this?
I don't know.
Well, I think it'll compare it to the harmonic pretty good. Hardy har. The harmonic series nth term is 1 over n. And now my question is this bigger or smaller than 1 over n? How does 4 over 2n plus 3, all right, is it bigger than 1 over n?
Yes.
For all values of n, at least for values of n greater than 1. So let's plug in 1. 4 over 2 plus 3 is 4/5, or 0.8. Is that bigger than 1 over 1?
No.
No, not in that case. Well, that's for when n equals 1. I guess I'm supposed to try only the ones greater than 1. Let's plug in 2. 4 over 2 times 2 is 4, plus 3 is 7. 4 sevenths, is that bigger than 1 half? Yes, right? Because 3 1/2 sevenths would have equaled a half perfectly, so 4 sevenths is bigger than a half. Okay, so that's true. Let's plug in 3 just to verify. 4 over 9, 0.4 repeating, is that bigger than 1/3? Right, 0.4 repeating is bigger than 0.3 repeating. So it appears as though this is true, all right? And since I've shown that my series terms are bigger than an already known divergent, all right, I would conclude that our series is also divergent. All right, so it's a little bit finicky to get used to. And I guess like the thing that takes a little bit of skill is trying to figure out which of these should we compare it to. You know, like that's the part that's a little bit tricky. Let's see, I think I can fit one more.
So the harmonic you just showed us, was that like the smallest possible harmonic?
The smallest possible divergent series, something like that?
Yeah.
It seems like it's pretty darn close. I would say, based on my initial analysis, I'd say yes. But yeah. Let's see, 4/5 was that one. Let's do another example. Let's do 1 over 1 squared. 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared.
Hang on.
Yep. Now, large denominators are good, right, for convergence, right? Large denominators mean smaller fractions, right? So, and I believe we had someone recognize the pattern for the numerator skillfully. They said the numerator appears to be 1.
How did you do that?
Actually, I think the numerator is actually n to the 0. So close, I'm sorry. I'm just kidding. Classic. Let's see. And the denominator, it appears as though it's something squared. 1, 3, 5, 7. What kinds of numbers those are?
2n minus 1 squared.
Those are, well, 1, 3. If it was prime, it would have had to have a 2 in there. And actually, prime would be really difficult because I couldn't make a pattern for prime numbers. And we talked.
Me.
Yeah.
We couldn't find
Yeah.
whether.
That's what I'll have to do. I'll give you a series of prime numbers being the pattern. But I bet we could do it using a comparison test. Well, man, that would be tricky. Wow. Anyways. Wow. I don't want to complicate things any further. But wow, 2n minus 1 appears to be the pattern. You guys are pretty quick on the odd numbers, right? So the difference was 2, so 2n I knew it was going to be, and then it was just an offset. 2 minus 1, 4 minus 1, 6 minus 1, 8 minus 1. By the way, the definition of odd numbers are numbers that fit the pattern 2k minus 1, where k is an integer. And the definition of an even number is a number that fits the pattern 2k, where k is an even number. Wow, I've mentioned 2 video game companies, both, 2K and Harmonix. Both of them had studios in Boston. Wow, and wow. Something going on here. So let's see. So what series do you think this compares to? What would be a good comparison? I think number 5, where my p-value would be 2, right? So let's see. I'll just call this number 5 or whatever. So a sub n equals 1 over, what is it, n to the, I'll call it second, is what I'm comparing. N to the 2. So let's ask our question, is 1 over, man, that's a terrible vinculum, 2n minus 1 squared, is that going to be, do I want it to be less than or greater than this?
I want it to be less than that.
It has to be less than that because this is a convergent series, and if it's greater than it, then I know nothing. All right, or yeah, nothing really. So let's see. I'm hoping that this is less than 1 over n squared. So that's the question. So I'm going to kind of, well, you could justify this a couple different ways. Is 2n minus 1 going to be bigger than n for all n greater than 1? Well, let's try it when n equals 1. I always find it interesting, even though you're not supposed to consider when n equals 1. I like to consider it anyway, because usually that's the one case where it might be bigger or equal or something like that. So let's see. And I think if n is 1, yeah, I think those happen to be equal, right? 2 minus 1 is 1, 1 squared is 1, and 1 squared is 1. They happen to be equal when n equals 1. Question, comment? Yeah.
In the quizzes and homework and whatnot, will we be given series 2
This list?
these two?
Sure, because I'm a nice guy. Because I am a nice guy.
Actually, they have to memorize every single divergent and convergent series that there is. Ever.
Man, 1 over the prime numbers. I think it'd be convergent. Because prime numbers are eventually going to get so far apart from each other.
Because the higher you get, the more.
Yeah. So let's plug in 2 for n. 2 times 2 is 4 minus 1 is 3 is 1/3, or 0.3 repeating. Is that less than 1/4? Wait a minute. What did I just do wrong, guys? 3 squared is 1/9. Right. There we go. Is 1/9 or 0.1 repeating? Is that less than 1/4? And yes, 0.1 repeating is yes. And then let's check another one. Let's check 3 real quick. 2 times 3 is 6 minus 1 is 5 is 1/25. Less than 1/9? Yeah. So I'm saying this is true, and therefore, we're talking convergence here. Convergence! Yes. All right. So that's the idea. You've got some comparisons. Actually, I think. Watch how well planned ahead I am. This might spoil some of.
Oh, we're doing the triangle pyramid thing?
Well, this is a little formula sheet I'm going to give to you guys today. I've got your arithmetic formulas. I've got your geometric. I've even got S sub infinity there. And then I've got our summary of series for reference, which are the ones there. So tells you which ones are convergent, divergent. And then some stuff that we'll do the next couple days. Man, look how beautiful that is. Isn't that great? Look at this. Cosine of x equals this. Equals. We're relating trigonometric ratios to sums of infinite lists. What? Mind blown. Okay, anyways, that's enough. Bye, Internet.
Maybe if we get